This is the first video in a series on p-adic numbers. And I thought I would talk about these partly because I'm interested in them as someone who likes number theory, but also I think the current resources on them leave some things to be desired. A lot of them are pretty dense in the theory, and they also don't give a lot of applications that are accessible to a very wide audience. So I thought I would start out by explaining the basics of what p-adic numbers are and give a few examples of ways in which they're useful and what kinds of things mathematicians use them for today and what advantages they have over other number systems. Okay, so first of all, well, the most straightforward but perhaps most naive way of defining a p-adic number is just to say that it's essentially a base p expansion, or p is a prime, except that we can go infinitely far to the left. So usually when we're talking about base p, we go to the right, and we might allow ourselves to go infinitely far to the right. So for example, in base 2, you might have something like, well, an infinite sequence of 1s, and that will end up being, well, a half plus a quarter plus an eighth, and so on. So you get a geometric series, and that equals 1. So even then you already have this weird example of having two very different ways of writing the same number. But we'll return to that in a little bit when we talk about p-adic numbers in more detail. So an example of a p-adic number, maybe with 2 as the prime, would be something like 1 plus 2 plus 4 plus 8 plus 16, and so on. Okay, so of course this does not converge in the usual sense, but it does converge as a 2-adic number. So if you wanted to, you could write it as something like this. Okay, so it looks pretty weird when you write it like that, but we're just adding up all the powers of 2 from 1 on up. And now you might have seen something like this before if you were talking about convergence of geometric series, and in high school or whenever people first learn about geometric series, the condition on convergence is that the common ratio has to be less than 1 in absolute value. So in general you have something like this. So the sum of all the powers of r is 1 over 1 minus r, but this is only true if r is less than 1 in absolute value. So it definitely doesn't make sense in the usual real numbers if we're taking r to be 2. But if we suspend our disbelief for a moment and just blindly plug in r equals 2, we would get 1 plus 2 plus 4 plus 8 and so on equals 1 over 1 minus 2, so we get -1. Well, maybe I'll put a question mark there because it isn't quite clear what that means. But this is true in the 2-adic numbers. So well, before I explain how that makes sense, I first have to give a more rigorous definition of the p-adic numbers. And maybe I'll say a bit about the history as well. So it started with a mathematician named Hensel, and this was around 1900. It was his first paper on it was, I think, in the late 1890s, and he was motivated by trying to find some way of carrying over tools from analysis to number theory. So in analysis, you might have something like an infinite sum of an x to the n, so a power series, and he wanted to get some kind of connection between that and number theory, or something, some kind of object that functions in the same kind of way as a power series. So perhaps the most obvious choice would be to let x be some kind of integer and maybe the an's be integers. But then of course this leads to the question of what on earth something like this would even mean. I'll say in a little bit why we take p to be a prime and not just work with any old integer. Okay, we definitely don't want to use 1 as the base, or 0 or something like that, but we can use bases that aren't prime, but it ends up being most convenient to use prime bases. So that was Hensel's idea, and it actually took some time for mathematicians to accept it, not surprisingly, perhaps, because it's definitely a strange concept when one first sees this, and it seems like it's total nonsense, perhaps. But after a few decades, mathematicians were able to make it more rigorous, define it in terms of axioms rather than just kind of saying, okay, take this nonsensical looking expression and do some things with it. And then also mathematicians started using these p-adic numbers to prove some interesting results. So perhaps one of the first interesting results in this direction, I think this was around 1920 or maybe 1917 actually. Ostrovsky proved that essentially the p-adic numbers, so these are usually written qp, and the real numbers are in some sense the only extensions of the rational numbers. Actually, they're the only completions of q with respect to some absolute value. So I'll say more about what that means. But roughly speaking, the real numbers are what you get when you take all possible limits of sequences in Q with the usual absolute value. So the usual distance, absolute value x minus y is, well, that's the distance between x and y in the usual sense. But if you do this with a sort of p-adic analog of that, which is usually written with a little subscript p, and you take all possible limits of sequences of rational numbers with respect to that metric, you end up with qp. So there are a few different constructions of the p-adic numbers, but they all lead to the same kind of object. Now, just a few years after Ostrovsky proved that these are the only completions of Q, Hasse proved one of the first results using p-adic numbers to prove some property of number theoretic objects that were interesting in their own right. So the idea, it later became known as a local to global principle. Now what that means is, well, the p-adic numbers give information about primes. So if you pick a value of p, you're sort of focusing on one particular prime, and then you can vary p if you like, and that will give you, well, an infinite amount of information. But if you're trying to solve a problem with rational numbers, you can think of the rational numbers as being part of QP for every p, and then try to solve the analogous problem in QP and see what happens. So the idea is basically you have a problem that you're trying to solve over Q, and what you do is you embed it into every QP. So what you end up with is an infinite number of problems over every QP. Okay, so this sounds worse, but it's actually often much easier to solve the problem in p-adic numbers. Okay, and you also often want to include R or maybe complex numbers as well. So a simple example would be, say you're trying to solve an equation over the rational numbers. So in Haas's case, he was trying to find solutions to certain kinds of equations with rational coefficients. So he was looking in particular at quadratic forms, so something like a1 x1 squared plus a2 x2 squared, and so on, and there can be some cross terms as well, but I'm just going to ignore those for now. And the fundamental question he was looking at was, are there values of x1, x2, and so on that make this thing equal to 0? And, well, okay, if all the x's are 0, you automatically get 0. So can you get 0 with any other values of the x's? So if the a's are rational, and you're looking for rational solutions for the x's, well, assuming there's a rational solution, there's certainly a real solution, because every rational number is also a real number. And similarly, the rationals can be thought of as a subset of the p-adic numbers. So any rational solution to the original equation gives a solution in every possible field on the right. So if you take a solution here, you get a solution in every QP and R, and C if you want, but we usually stick to R because that's the completion of Q with respect to the usual absolute value. So if you have a solution to the original thing, you get a solution in every QP and R. Haas's idea was to go in the other direction. So first of all, it's not even clear that you can go in the other direction, but that's what Haas studied. And so if we can find solutions in every QP and R, can we somehow piece them together to get a solution in Q? And this is called a local to global principle because you're looking at, on the one hand, local information about the primes and the usual absolute value, and you're trying to get some solution that works everywhere. so that would be a global solution. So in general, the QPs are called local fields. There are other examples of local fields, but these are the only ones we're going to be looking at in this series. And Q is an example of a global field. And there are other global fields as well, which are finite extensions of Q, which we'll take a look at. And then you can do completions of those, and those give other local fields. I don't think we'll get too into that because it gets pretty complicated pretty quickly, but a lot of the theory there is similar to the theory for QP. So we'll do most of the examples and theory for just the p-adic numbers. And then maybe toward the end of this series I'll say a bit more about how one would extend this to other kinds of fields as well. Now, the non-rigorous definition for the p-adic numbers was an infinite base p expansion to the left. And we can start with negative powers as well. So you could do something like a minus k p to the minus k plus a negative k plus 1 p to the negative k plus 1 with increasing powers of p. So it's sort of like a Laurent series in p. Okay, we won't quite do that because we need some way of doing things axiomatically so that we can be sure that the things we're doing are actually valid. So rather than doing that, perhaps the simplest construction of the p-adic numbers in a rigorous way is to use integers mod p and mod p squared, mod p cubed, and so on, and build things up that way. So we'll first start with z mod p. Okay, so if we're looking at a p-adic number without any negative powers, it would look something like a0 plus a1p plus a2p squared, and so on. So we're going to define what this means in a slightly different way. So what we could first do is take something in z mod p. So let's call it a0. And I'm assuming all these AIs are between 0 and p minus 1 to make it an actual base p analog, but there's no real need to have them stay in that range. They could be any integers. Okay, so if we take a0 in z mod p, that's sort of like a first order approximation, or I guess a 0th order approximation to this whole thing, a0 plus a1p and so on. Okay, so then what we could do is ignore everything beyond the p term, and that will give us a0 plus a1p. Okay, so in some sense that's a better approximation to the thing we want. So that will be something that is inside z mod p squared. Okay, and then we go one step further. Okay, and then keep going. So this is in z mod p cubed, and then the next thing will be in z mod p to the 4th, and so on. Okay, so rather than thinking of this as an infinite base p expansion to the left, what we're going to do is think of it as a sequence of numbers in z mod p, then z mod p squared, then z mod p cubed, and so on, where to get from one number to the next, you add something that's a multiple of a power of p. So one way of phrasing this more formally is if you think about reducing this number mod p, you get a0. If you think about reducing this number mod p squared, you get the previous thing. If you take the next number and reduce it mod p cubed, you get the previous number. So we have all these ways of getting from one group, or actually a ring, down to the next one, which is just basically taking mod whatever you need to take it. And all those are going to be compatible in the sense that if I have something far out to the right, so somewhere out here, and I reduce it mod something, it's going to give me whatever I had, for example, here, and everything is going to work out. So I'm just adding on higher and higher powers of p, so that forces this compatibility of the numbers in these rings. Okay, so what we'll do is, this is usually written zp. These are the, not quite the p-adic numbers, but they're called the p-adic integers. So those are the numbers without any terms before the a0. So these are really power series in p, rather than Laurent series where you can have negative powers. So zp, we can define it to be the set of sequences. So you might have something like x0, x1, x2, and so on. Okay, and it lives in this giant product of all these things, so I'm not going to write out the set that it actually lives in, but the condition is just that if we take, for example, xm and xn, those had better be congruent mod, well, whichever prime power is lower. So let's say p to the n if m is bigger than n. Okay, so that's just saying that we're taking a bunch of residues in these rings, but the higher ones match the lower ones if you reduce them. And then zp can be thought of as these power series in p, because x0 gives you the first term, x1 gives you the first two terms, x2 gives you the first three terms, and so on. So with this definition, it's a little less straightforward, but it's actually more useful in some ways because, for one thing, this is a well-defined thing, and the properties of the p-adic numbers fall out of this. You don't have to make sort of weird definitions and hope that everything works. And also, some of the computations are easier if you think about them in this way. Okay, but that's only the p-adic integers. To get p-adic numbers, you need to allow negative powers of p. Now, one easy way to do that is just to say, take all the ratios of p-adic integers. So we can define qp, which is the p-adic numbers, to be just the field of fractions of zp. Okay, now it's not totally obvious that that really is the same thing as just allowing negative powers of p, but certainly the field of fractions does contain everything that looks like a minus k, p to the minus k, and so on, because we can just divide through by p to the k, and then the numerator is a p-adic integer. Okay, so every p-adic number, as we've defined it using this base p idea, is a ratio of two p-adic integers. And it turns out that if you take any two p-adic integers, you can always write it as a Laurent series in this way. So the idea is actually not really any different than for power series. So if you have two p-adic integers, well, you do essentially what you do for ratios of power series. So if b0 isn't 0, then you can invert this denominator basically by writing it as a geometric series. So you write it as something like b0 minus negative b1p minus da 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 da, and then you turn that into a geometric series with this whole big mess as the common ratio. Now, if b0 does equal 0, well, then you have a factor of p in the bottom, but that's okay. That will give us some negative powers of p when we expand this out, but there's nothing wrong with that. So if we just start wherever the first non-zero coefficient is, we'll get some negative power of p out of that, and then the rest we can expand as a power series. And that's really all there is to it. So it's the same kind of argument that works for ratios of power series giving Laurent series. So if you take some field k, it doesn't matter what it is, and you take the power series ring, the field of fractions of that is going to be, well, it's written like this. The notation is pretty annoying, but the field of fraction of the ring of power series is the set of Laurent series. And the same thing goes for p-adic numbers. So this is one example of how p-adic numbers behave a lot like Laurent series or power series. And the similarities go much deeper than this as well. Because just like how the p-adic integers can be thought of as ways of taking integers mod p, then mod p squared, then mod p cubed, and so on, you could do the same sort of thing with power series with rational coefficients. So you think of polynomials as being approximations to power series. So you would start with a constant polynomial. Okay, so that's just something in Q. Pretty boring. Okay, but then you take the next worst approximation, which would be something linear. But you could think of that as a polynomial in x, but where you're modding out by x squared. So you'll end up with just something that's linear, or maybe constant. So Q can also be thought of as Q adjoin x mod x. Okay, so that's a silly way of writing it, but when you quotient out by all the powers of x, you're left with just constants. And then at the next level up, you have everything where you ignore x squared and beyond, and then you ignore everything that's x cubed and beyond, and so on. And again, this is a sort of completion, but where x is playing the role of p before. By the way, we won't really need to do too much category theory, I don't think, but the technical term for something like this is an inverse limit, where you take something in sort of the base ring or group or whatever kind of object, and then you lift it up to another kind of similar thing, and then just keep going. And then you get some kind of sequence of numbers, and they all have this sort of compatibility property that we were talking about before. So you have, x0, then x1, then x2, and so on, and then you have those live in some mystery objects. But if you go from 1 down, you get from x2 to x1, from x1 to x0, and so on. So this inverse limit of the z mod p to the n's is often written like this, or maybe with an n beneath the arrow. So that you can think of as a definition for the p-adic integers. And then the QPs are the fractions. Okay. Now that's the sort of most basic definition of what they are. But next time we'll talk about how to think of them in terms of completions. So we'll talk about absolute values, not just the usual one, but other kinds of absolute values as well, and how to get the p-adic numbers from that.